My name is Dr. Gwen Sturdivant, and I'm here to introduce the Goldilocks approach to randomizing clusters with confidence. This approach is used for cluster randomized trials, where the design requires groups or clusters to be randomized instead of individual people. For example, the clusters could be clinics or hospitals. Often, in cluster randomized trials, there are limited numbers of clusters to randomize. For example, instead of randomizing 5,000 patients, you might be randomizing 20 clinics with 250 patients each. Randomizing a small number of clusters means that treatment and control arms might end up with very different baseline values for some variables. One solution to this is to pair similar clusters to each other and then randomize one unit in each pair to treatment or control and allocating the other unit to the opposing arm. The Goldilocks application allows researchers to evaluate different pairs and explore their effects on the baseline balance for covariates of interest. We'll start by loading the data into the application. The application accepts data sets in Microsoft Excel format. The columns are variables we want to make balanced between the study arms, and the rows are clusters to be randomized. All the columns must be numeric. Next, we input some basic information into the application. The number of simulated randomizations we want to perform, the number of variables that are important to balance, and if there's an odd number of clusters to randomize, whether the unmatched cluster should be assigned to treatment or control. This tab is where the business happens. For each variable, there are 3 inputs. First, the maximum allowable mean difference between the arms. This value will appear at the top of the y-axis. Second, the weight of the variable relative to the other variables. And third, variable selection. When first loaded, the default max for the mean difference in all variables is 5. Each weight is 1, and numeric variables are selected in spreadsheet order. When we hit go, the application matches and repeatedly randomizes the clusters as described in the accompanying paper. See the link and citation in the text below. Let's look at a specific example. In the swap out trial, our researchers wanted to randomize 137 hospitals to one of 2 approaches to reduce all Staphylococcus aureus clinical cultures as a primary outcome in ICU patients. Our example has 3 variables. These variables are monthly ICU days, Staphylococcus aureus cultures per 1,000 patient days, and MRSA cultures per 1,000 patient days. I will show how we get figure 1 from the article. Trial designers decided that the maximum mean differences between the arms were 60 monthly ICU days and 0.15 difference in both Staphylococcus aureus MRSA cultures per 1,000 days. These maximum differences should be initially developed a priori, but can be modified to find an acceptable balance in the trade-offs between variables. I called this the Goldilocks approach because the user can change their acceptable parameters in an iterative process to find the right trade-off for matching and randomizing their available clusters. This iterative process is similar to that undertaken in the well-known children's fable, which involves 3 attempts at identifying suitable porridge, chair, and bed. Our experience has been that multiple simulated randomizations can influence weighting such that the ultimate randomization draw is far more likely to be balanced when actual randomization occurs. In figure 1 from the accompanying article, the plot in the upper left-hand side has weights of 1 for all 3 variables. In the plot, you can zoom in by dragging and clicking. In addition, color is used to display higher values instead of a dark, bold line for the mean. Finally, clicking on the plot near a y-axis redraws the plot with updated color scheme and shows how randomizations with poor balance for that variable fare for that other variables. Researchers using the Goldilocks approach found that unequal weighting of the 3 variables achieved better balance. Some randomizations have between-arm difference for Staphylococcus aureus cultures that are greater than the maximum. To reduce these differences, we try new weights of 1, 8, and 1. This forces pairs to have more similar values for Staphylococcus aureus cultures, and when randomization occurs, the treatment and control arm should have closer means. Unfortunately, this matching has consequences, and the other two variables of interest are less well balanced. With weights of 1, 4, and 2, the mean differences are within the bounds for all three variables. Once researchers are satisfied with the average differences between treatment and control arms, this allows them to share the differences with others. Input the file name, your name, select either PDF or Word, and click the button. The file will download and include a plot, the variables used to match clusters and their weights. This is a good way to share proposed rates with others. We recommend consulting a statistician prior to randomization. To randomize a trial, a seed is generated. The seed is important, so record it. Labels for each arm can be input too. The randomize button will randomize clusters to each arm. Prior to randomizing, users must have first clicked the red button here. To download the final randomization plot, input a file name and click the button. This will result in a plot with the actual randomization in red and other possible randomization in gray, as well as a table with each cluster and the arm label you input earlier in the matches. I hope this is helpful, and thank you very much for watching and reading this article.